So I shall be discussing two problems in pure rotation, and I shall go through them slowly because these are very standard and very important examples. The first one is called a physical pendulum, and it is quite simple, but we shall take our time and write the equations that we know in very different ways just to see whether we're comfortable with writing the various forms. So a physical pendulum is pretty much like the simple pendulum, but the difference you will notice very quickly. Now this is a simple pendulum. It has a length L and there is a particle mass m, and as opposed to, and it oscillates back and forth, as opposed to a physical pendulum, which is now one of our favorite examples. Let's say a meter scale is pivoted at one point and made to rotate back and forth by a displacement. So here's the pivot, and the pivot is an axis which is perpendicular to the board and passes through this point, and once that happens, then it's pure rotation about that point. But this time it's not a mass, but it's not a particle mass, but a rigid scale. So this is our classic simple example. So can we write accurately the equations describing the motion of um, these two objects? So this is the center of mass. So before we jump to making predictions about the rigid scale, might be a good idea to go back to the simple pendulum and revise things and know whether we know what we're talking about. So one thing is for sure, we do know that the pendulum is a little bit tougher than it looks, because it is, the easy part is that it is circular motion, and the tough part is that it's non-uniform circular motion. So what we used to do is getting some answers from the conservation of energy. So how does one get the answers from the conservation of energy? What is the reason why the conservation of energy works very well? And now because it's a point mass, one can write down the forces. Now there is a tension, then there is gravity. And the important, nice, beautiful observation in this case is that the work done by the tensile force, is zero, and the reason for that is that the displacement is always perpendicular to the tensile force. So the work done by the tensile force is zero. Now that leaves gravity, and it is easy to calculate the work done due to gravity because it does not depend on the path. So one way to write the whole thing is work done by gravity is equal to the change in kinetic energy, and we've used this simple relationship to solve some interesting problems. But we can also write this as kinetic energy plus potential energy is equal to constant, because there is no friction and the forces are conservative. Okay, but having said all this, we know the limitation of this whole approach, and that is that we don't have an idea of the time. So is it possible to also make predictions about at every instant of time? Of course yes, and we know how it's done. The way it's done is we use Newton's laws. So can we write down the Newton's laws today? Today it's possible because we have our kinematics is now a little bit better developed, and with respect to circles, and you see that it is going to help us to solve this problem, and that is why we are picking up the simple pendulum at a slightly later stage as far as Newton's laws are concerned. Okay, and the reason is now that it is a definite circular motion, but it's a constant radius, and we do have some formulae for the constant radius, and we're going to now exploit it. So the way to exploit it is look at any instant of time. If theta is the displacement, the radial the angular displacement, and we know that this is rotation. So what we do know is that at that instant there are two components of the acceleration. The one towards the center is called a radial, and that is equal to L omega t at that instant whole square, and we have derived this, so now it's time to use it. At is equal to L into alpha t, where alpha is the angular acceleration, d omega by dt. And if you just want a quick reminder of what it is. Okay, so here we go. Things looking very good. Now how can we use this? At that instant, what are the forces, external forces on this? So there's one force for sure, which is towards the center of the circle, which I'm going to call it T. And then there is the force of gravity, mg. But what we are going to do now is we're going to resolve the forces along this axis, and I think you know why. Because we have formulae along these two axes. I mean, let's call this the tangential axis, and that's called the other one the radial axis, and they're perpendicular to each other. Right, so we're interested, and now it's also easy to T is particularly friendly. It's already in the radial direction now, but here is my first real computational step. I'm going to break up this mg along the tangential direction and along the radial direction, and perhaps you will agree very quickly that this is theta. Now that means that the radial direction forces, this one is mg cos theta, and already I'm ready to write an equation which is coming straight from Newton's law. At that instant of time, T minus mg cos theta, mind you, I'm writing the force towards the center of the circle, that's why T gets a positive sign, mg cos theta gets a minus sign, is equal to the acceleration in the radial direction, which happens to be this. This is what we have done, and we're going to use it now, and now you'll realize the importance of all the kinematics that we have done. So T minus mg cos theta is equal to mass into acceleration, which happens to be L omega square t, and this is a beautiful equation. And now we'll have to figure out whether it's useful or no, but that's a different story. The fact that we're able to write Newton's laws fairly easily like this is pretty good. Theta is changing with time, omega is changing with time. This is an instantaneous equation. What about the equation in the other direction? This force is mg sine theta. That's simple resolution, and that force is related to causing this acceleration, which is pretty good. So let's write, what should we write? Mg sine theta t at that instant is equal to L into d square theta by dt square. Mind you, I've written alpha is d square theta by dt square. So this is another interesting equation, and I just want to highlight the fact that we've written down two equations, and now let's see how useful it is. Now comes solving these equations, and what's the significance of solving this equation. I am not going to solve it because it's unnecessary. The mathematical techniques to solve these equations are unnecessary, but in principle this equation can be solved, and you can get theta t and omega t as a function of time by solving this equation in principle. Now what that means is that you can put the value of omega t into this equation, and you already know theta t, and therefore you can calculate the tension. Mind you, tension is also a function of time. So here we go. From whatever I've written on this board, it's looking a little cluttered, but I think what we're trying to say in principle is that this is solvable, this is solvable, and t is solvable. And all the three unknowns are what we are looking for. So is t as a function of time important? Yes, because if you were to design the string, then t as a function of time is important. So I repeat. So what have Newton's laws given us? They've given us theta at every instant of time, omega at every instant of time, the tension at every instant of time, and you can see what you mean by a complete piece of information is possible from Newton's laws, but you have to solve these equations. So mind you, these equations can be routinely solved by a computer, and we are not discussing that in this part of the course. What we are really worrying about is, can I write the equations of Newton's laws? And that part, if you can say that it's easy, then we are in business. Now how about using a more recent law that we have learned? Tau is equal to I alpha t. So is it that um, is it are we going to get something else or something new out of this? Well, let's see. Um, so just want to quickly remind you that this is a particle in motion, and the chances are very high that since the problem has already been solved completely by this whatever we've written here, it's very unlikely that we need any other information. But one would like to see what this equation is going to give us. So let's see. So here I go. There is a mass, and it is rotating in a circle. And what is the moment of inertia of a single mass, m1, with the radius L? We know it. It's m. Um, sorry. The moment of inertia is mass into L1 square, L square, sorry, L square, mass into L square. What is this? This is the moment of inertia. Now offer m1, which we derived last time. Now just to remind you that the axis, what is the, this is the pure rotation, and this is the axis which is perpendicular to this point and perpendicular to the board, and it's a pure rotation. So I got I, and so what is tau? Let's try tau. Tau is, there's only one force, or rather two forces acting on mass, and which is the tensile force and the gravity force. And one quickly realizes that torque due to tau, okay, let me write it here, torque due to tension is equal to 0, and the reason is that the tensile force passes through the origin. Okay, T passes through origin. We have figured out how to find the torque, and T does not contribute. And what does mg contribute? How does mg contribute? I think you will readily agree that mg, the force into this perpendicular distance, into this distance, is going to be the torque. So this is the perpendicular distance we are looking for, which is L sine theta. This is L sine theta. Okay, so do it whichever way you like, r cross mg, lg's mg into perpendicular distance, and so on. So we have mg sine theta as the torque due to gravity at that instant. Theta is a function of time, torque due to gravity. And if we put these two together, then torque is equal to I alpha, and I, by the way, is ml square. We have mg sine theta is equal to ml square into alpha, and if you cancel out m, one second, I'm sorry, I made a mistake here. mgl sine theta, I'm sorry, mgl sine theta, so L, and one L will get cancelled, and we have L into alpha is equal to g sine theta. And I want you to see that this is pretty much the same thing at that instant of time. at that instant of time is pretty much the same equation that we wrote here, here. Okay, so it's pretty much the same equation that we wrote here, and that means that we haven't got anything new. Nevertheless, it's nice to know that everything fits in without any contradictions. And um, so can we also do this complete set of equations for a physical pendulum and analyze what we have, what are the quantities that are important for us, and that we can calculate as a function of time, and that means that we're making some predictions. So this is our job for the next video, and what we have done here is try to do the same, answer the same question for a simple pendulum, and you can see that a simple pendulum is not as easy as it appears. It's definitely not simple, but a lot to teach us. Okay, so let's stop this here, and let's talk about the physical pendulum in the next video.